Hello everyone, and welcome to Terraform for the largely uninitiated. I'm going to assume you are all largely uninitiated. If there are any experts in, do please come up and talk to me afterwards. And don't ask me any taxing questions in front of everybody else, thank you. So, I was talking to my wife about this presentation, and she said, in a presentation, everybody hates icebreakers. Like, talk to the person next to you. Everybody stand up. Everybody put your hands in the air. So with that in mind, everybody put your hands in the air, please. Thank you, thank you. It's as much for me to make sure that I'm paying attention as everybody else. Now keep your hands in the air, keep your hands in the air. I haven't given the other instructions yet. So, if you have used Terraform in production, then please put your hands down. Okay. If you've tried Terraform out, just played around with it, then put your hands down, please. If you've used another infrastructure as code tool, then put your hands down, please. Okay. If you have still got your hands in the air, then please put your hands down. Thank you. Okay. So Terraform, it is an infrastructure as code tool. It uses a declarative language to describe your cloud computing resources and what you want those to look like. But what does that actually mean? And more to the point, why should we actually care about that? So cloud computing providers or infrastructure as a service providers have changed how technology companies manage their servers. Your fledgling startup does not need to spend tens of thousands of dollars anymore on servers and space in a data center and somebody to plug cables into them and somebody to put an OS on them anymore. You open an account with a cloud provider, such as AWS. Other cloud providers are available, of course. And with a few clicks in their web console, you have your very own server at your disposal. When you're finished with it, you can shut it down. It served its purpose, and you no longer pay for it. Creating infrastructure like this is really easy, but it doesn't scale when you need it to. So what we can do is to use code to drive that process. And then you can scale that code in the same way that you would do other software that you write. And that is what you call infrastructure as code. Why doesn't the easy method scale? So when you open an account with a cloud provider, you generally find yourself in their web console, perhaps being guided through how to do something. It's a great way to get started, and with a few clicks, you can find yourself in the driving seat of your very own server. To add a second one, all you do is repeat the same process. But to do that, there are several steps in the process. And in AWS, those steps include choosing a machine image for the server with the base OS on it, deciding what size of instance you want, how much CPU, how much RAM you're going to assign to it, what kind of storage type you're going to have, how big that storage type is going to be, network security groups that you're going to add to it. So maybe only port 22 is going to be open from your local IP address. Oh, and we need to add SSH keys, of course, if we're going to be able to connect to it over SSH. So are you going to get that right every single time? And what about when you need to add 10 servers, or more than 10 servers, 100 servers, something like that? When different people try to follow that same process at different times, then things can really diverge. Meet Bob. Bob is an engineer. And Bob creates a virtual machine, and he calls it application 01 because it's running the main application. Seems fine. He gives it 8 gigabytes of RAM because that was the default given to him. He didn't really think about it, but nothing's on fire, so Bob's pretty happy. Meet Alice. Alice comes along, and she notices that the VM that Bob created is struggling a bit under the volume of the requests. So Alice creates 2 more virtual machines, and she gives one of them 16 gigabytes of RAM because the 8 gigabyte one was struggling a bit. And she intends to do the same with the second one, but accidentally clicks in the wrong place and gives it 4 gigabytes of RAM. She creates a load balancer, and she registers all those with the load balancer. And these are running the web app, so they're called web app 1 and web app 2, which is a bit different from the naming convention that Bob chose, but she's in a hurry. Things aren't on fire, but they are smouldering. Along comes Barry. Barry's third day on the job, and he's poking around in the web console, and he notices that this load balancer's got 3 instances behind it, but one of them clearly doesn't belong there. It's got a completely different name to the other 2. So hurrah! Hurrah for Barry. It's only his third day on the job, and he's found a mistake that he can correct. People are going to be very pleased with Barry. So Barry removes application 01 from the load balancer. It definitely shouldn't be there. Takes it away. But when he does that, the smaller instance that Alice created starts to struggle under the volume of the requests. And soon, the load balancer marks the application on there as unhealthy, and it takes out the load balancer. So then we've just got one server handling all these requests, and that starts to struggle as well. And soon the application's completely unresponsive. Customers are calling up to find out what's happened. They're asking for their money back. They're asking for Barry to be escorted from the building, and rightly so. So it's very easy to say, just don't be Barry. And I'm sure Barry probably feels like that at the moment. But this was doomed from the outset. This was a manual, multi-step process given to humans to do. So that's never going to end well. Cloud providers have an API to allow you to control resources in your account. And the majority of them also provide SDKs in popular and well-known languages like Java and Python, and even languages like PHP and JavaScript. So you can use these APIs and SDKs and write code to drive your virtual infrastructure. So you can use a language that's familiar to yourself, and you can use the power of the language to ensure that things are named consistently and things are secure. So now that everybody's sold on infrastructure as code, let's come back to Terraform. Terraform is an open source infrastructure as code tool from the HashiCorp company, and it allows you to define in code what you want your virtual infrastructure to look like. It supports all the major cloud providers, AWS, Google, Azure, plus support for lots of other cloud providers as well. It's extensible and open source, so people from the community can contribute code for providers that they need to use. Anything, really. I found this provider for the Domino's API, so you can order pizzas using Terraform. Not quite sure what the use case for that is, but it exists. So Terraform interprets the code that you write, it talks to your cloud provider, and it creates the resources that you asked for. If you need more servers, or if you need a database, you just add those into the code, you run Terraform again, and you get what you've asked for. Terraform uses a domain-specific language called HashiCorp Configuration Language, or HCl, to express what you like. It looks a little bit like Nginx config and a little bit like JSON, so it shouldn't be too difficult to work out what's going on there. This is a very simple example which shows defining an EC2 instance on AWS. And we'll come back and look at this in a little bit more detail. The HCl code gets interpreted by Terraform. It gets translated into calls to an SDK or an API to the cloud provider. It goes away, and that bit is abstracted away from you. You don't know, and you don't need to know, and you don't care how that happens, just as long as it works. And no matter what we're provisioning in AWS or another cloud provider, we express it in HCl. So I've said that HCl is declarative. What does that mean? So languages are usually in a category of being declarative or imperative. And imperative languages tend to be a list of instructions of exactly how you want to get to the end solution, whereas declarative describe an end solution. So if you think of a shopping list, if you give somebody a shopping list, which is a list of how to get to the shops, a list of instructions, how to get to the shops, how to actually get into the store, which aisles to walk down, which shelves to reach up to, and all the other kind of minutiae of performing a successful shopping trip, then not only are you an insufferable micromanaging control freak, but you've also written the world's first imperative shopping list. Whereas a normal shopping list would have Dom Perignon 2006, baguette, camembert, and you would just hand that to somebody. You don't care how it gets to you or where it comes from. You've just described an end state that you want to be in. So coming back to our example, how do we actually do this for real with Terraform? I'm going to have a little look at some of the different components of HCl that Terraform understands. So up at the top, we've got a variable, which we've called server name. And this is a variable which Terraform can take as an input, and then you can use the value of that variable in the HCl code. You can specify defaults for variables as well, and it's probably not too much of a mental leap to imagine another line on description with default equals and some string. And then we've got the resource. This is our AWS EC2 instance. All the resources are prefixed with the cloud provider that they refer to. So this one is AWS underscore. Everything in AWS would be AWS underscore. Likewise in GitHub, everything would be GitHub underscore. And then it's got a name that you use to refer to it in the HCl, which is example here. And then you've got a list of properties within that. So the AMI, the instance type, and we've got a nested block of tags there where we have referred to the variable that we defined earlier. So that's giving the name to the server. And I'm sure you can imagine that there could be multiple tags in there as well. And then finally, we've got an output. And again, we've referred to the resource from earlier on. We've got the ID of that. And that output will be printed at the bottom of Terraform's output. So that'll be things that you maybe want to use straight away. So you could, for example, output the IP address of the instance so that you can connect to it. And it saves you going and digging around in the console to find that. So all of your HCl code goes into a file with a .tf extension. And if you run Terraform in that same directory, then it'll be able to find that .tf file and understand it. And you can split your code into multiple .tf files, and Terraform will just smoosh those together and treat it as one big definition. So a common organization is to have a main.tf with all of your resources in, your outputs in outputs.tf, and your variables in, well, I'm sure you get the idea. But you can have as many .tf files in there as you want. So maybe you have all your IAM resources in an IAM.tf and your load balancer in a load balancer.tf, or everything in main.tf. It's up to you how you want to organize that. So Terraform needs to talk to AWS to be able to do any of this. And the code for actually talking to the different cloud providers is distributed separately to Terraform Core. Because Terraform supports about 100 different providers, it doesn't bundle all the code to talk to all of them when you download Terraform itself. So to be able to actually talk to anything, you run Terraform init in the same directory that your .tf files are in. And that parses the .tf files and figures out that you are wanting to provision resources on AWS because of those prefixes. And then it'll go away and it'll download the provider plugin for AWS. So now we're nearly ready to actually talk to our cloud provider, we need to provide some credentials to AWS so that it can actually contact the API. And for most of the providers, there are a couple of ways of doing this. One is a provider block inside a .tf file, and you provide your, in the case of AWS, your access key and your secret key and the region that you want to talk to. You can also use environment variables. I personally prefer to use environment variables because it reduces the chance of you accidentally checking in some secrets, and it's a very common way of passing credentials to other things, so it's a known pattern. It's less HCl code to maintain. You can parameterize these, of course, as variables, and with the AWS provider, it does support the other AWS mechanisms, so a credentials file in your home directory, or an IAM role on an instance for anyone who's familiar with those. So now we're actually ready to talk to our cloud provider. Terraform has a really nice mode called plan. You run Terraform plan, and it doesn't actually make any changes, but it tells you what actions it's going to take. It parses your code, and it checks the syntax, and it makes sure it's got enough information to actually be able to perform those actions. In this case, we need to pass a value for that server name variable. So we do that with a -var flag. There are a few ways of passing variables. They can be in a file, and you can pass it with a -var file, or there is a magical terraform.tf vars file that you can use, which will pick up automatically. But here we've specified a value for server name there. Terraform looks at what resources you've requested, and it says what is going to be created, updated, or destroyed. And of course, as we don't have anything, everything is scheduled to be created. And if you're happy with that plan, and let's face it, that plan is going to be considerably more comprehensive than the one that the UK currently has for leaving the EU, I think we'll all agree, then you can go ahead and apply those changes. So you run Terraform apply. Now, when you run Terraform apply, it'll first run through the plan again, but we'll come back to that. And then it'll say, is that OK? And of course, you confirm. And if you confirm that, then Terraform will actually go away, and it will create the resources that you requested, and it'll tell you what's going on as it's going along, and then it'll tell you what it did at the end. And of course, you've got the outputs. So we've got the instance ID that we requested there. And I did say that you don't have to run through that plan. So you can run Terraform plan, and you can save the steps of that plan into a file. So then when you pass that to Terraform apply, it won't run the plan again. It'll just say, OK, I'll use this plan that you've given me. I'll just run through these steps. So then if we make a change, see here we've changed the server name, and we are asking that to be persisted into a plan file. And it's saying that this is actually going to be updated in place. And the plan is going to be saved there. And then to apply it, you run Terraform apply and just pass it the name of the plan file. And this is where the declarative nature of Terraform really comes into its own. Because you make an adjustment to your shopping list of AWS resources. You just say, I want to add this resource, and you put in another resource block, or you take a resource out, or you modify some of the attributes on a resource, and Terraform will just work out what steps it needs to take to get from the reality of your infrastructure to what you've actually asked for. So one of the first things it does is actually check against the current state of your infrastructure. So when you successfully create a resource in Terraform, it persists the details of that into its state. And by default, its state is just in a file in the same directory that you ran Terraform in. So, Barry. Barry's been into the web console, and he's changed the name manually of one of the servers. So when you run Terraform again, Terraform will look in its state file, and it'll say, oh, I've created an EC2 resource before, an EC2 instance. I'm going to take the ID of that, and I'm going to look it up in AWS. And the name that I've been told it is not actually the same now. So I'm going to refresh my local state, and I'm going to tell you what actions I need to take to get back to the resource that you've specified. And then we go away and we have a word with Barry, and we say, Barry, please stop that. So we've looked at quite a simple example so far, but after we had a word with Barry, he went away and did some AWS training. So he now understands a highly available architecture in the cloud. And what he wants to do is to create a VPC. And he wants to create 2 subnets in each availability zone in this region, a public subnet and a private subnet. And there are 3 availability zones. There's 3 availability zones in this region. For those to be public or private, he needs to add some rules into the routing tables of the VPC, and he needs an internet gateway for the public subnets to talk through. He wants a minimum of 3 EC2 instances to be running in the private subnets, but he doesn't want to have to manage those himself, so he's going to use an auto-scaling group. He's going to hook up some CloudWatch alarms to that auto-scaling group, so if the CPU on those instances is above, say, 70% for about 5 minutes, then it'll add more instances in. He is also going to provision a multi-AZ RDS database, again in the private subnets. And he's going to provision a load balancer, an ALB, in the public subnets, which is going to point at the EC2 instances. And he's going to have a Route 53 DNS record, which is pointing to that elastic, to the ALB. So the eagle-eyed among you will spot that there are quite a few dependencies in here. The subnets can't exist until the VPC exists. The auto-scaling group can't launch any EC2 instances until the subnets exist. Likewise, the database can't be provisioned until there are subnets for it to sit in. The Route 53 record can't point at a load balancer unless that load balancer exists. So there are a lot of dependencies in there. Now, when you're writing HCl, you're implicitly specifying your dependencies when you're referring to different resources. So here we've got a VPC, and we've got a subnet, which is going to live inside that VPC. And in order to create a subnet, we have to tell it what VPC it's going to live in. So we have to pass the ID of that VPC, and we do it by referring to the VPC resource, which is above. So HCl allows you to do this, and you can and should use these references in your HCl code, because this sets up the dependencies. And because of these relationships between the different resources, Terraform can generate a dependency graph. So when you run Terraform and it parses your resources, it builds a graph in memory of all the resources specified. And starting at the root, it can walk that graph, and creating those resources there ensures that any dependencies are already met once it gets further down the tree. And because of multiple branches in the graph, it also allows Terraform to do a lot of operations in parallel as well. So most languages allow for some degree of code reuse, and HCl is no different in this respect. Modules are how Terraform reuses code. This is an example of calling a VPC module. And calling a module is analogous to a function call in another language. It has some inputs, and then it goes away and it does some stuff which is abstracted away from you, and then you might get an output from it as well. A module is just a directory of .tf files. It has variables, which are the inputs, and then it has resources within that, and then it can have outputs from it as well. You can refer to them locally in a local directory, but you can put them in remote locations as well, which of course makes it easier to share between different projects. So the early one we saw was in the Terraform Registry, but they could be on GitHub, they could be on Bitbucket, GitLab, S3. Terraform understands quite a lot of different remote locations for those. Modules are downloaded when you run Terraform init. So if you add a module into your code, having already run Terraform init, then you'll need to run it again for Terraform to be able to download and use that module. Or likewise, if you want to update the version of these modules, then you need to run Terraform init again. So, Barry. Barry could write that entire VPC definition himself, and I'm sure he would do a great job. But we might not have to do that. Reusing Terraform modules, reusing other people's code is easy with the Terraform registry. So the Terraform registry lets you search for modules within there. You can publish your own modules to there, but you can consume other publicly available modules from there. And so in this case, it would be really handy to use the verified AWS VPC module from the Terraform registry. And then we can avoid having Barry write that all by himself. Not that we don't have faith in you, Barry. As well as variables, resources, and modules, HCl also has something called data sources. And data sources are a way to fetch information or compute information in HCl. So this example here is querying AWS for the latest Ubuntu AMI to provision an instance with. So that allows you to filter on ones owned by Amazon, ones starting with Ubuntu, and asking for the most recent. And then we can refer to it in the same way that we do with other things, other resources and variables and things. We can refer to it and pull out one of its properties there. So there are some other things that I'm not going to talk about. The more complex bits of HCl. HCl does allow you to assign a count to resources. And that's kind of like a loop. So in your EC2 resource, you can put an attribute in there, count equals 5, for example, and that will go away and it'll create 5 EC2 resources. And that's quite a handy thing, but it's essentially a bit like a loop, and there are strange things that you can do where you refer to the index in there. You can do conditionals in HCl as well, ternary operators, and there are lots of built-in functions for manipulating lists and maps and things like that. It can get really quite complicated. Provisioners. Now, I don't tend to use provisioners at all. Provisioners are a way to connect to a resource once you've created it and, for example, execute scripts on it. So there's a provisioner for SSH, there's one for Chef, Ansible, Puppet, things like that. So when you've created your EC2 resources, you can connect to them and you can install packages on them and stuff like that. I don't tend to use those because I prefer to make my infrastructure immutable. If you're provisioning 10 or 100 servers, you don't want to be connecting to each one and installing packages each time. So I find it's easier to bake an AMI or create a Docker image for a service or something like that. but provisioners do exist. Terraform 1.12, Terraform 0.12. Terraform 0.12 is apparently going to be out in a few weeks now. The current version is 0.11. One thing which Terraform 0.12 does is to change a lot of this really complex HCl, particularly with counts and the loops, and to make that much simpler. So that's another reason I haven't talked about that. Terraform 0.12, it has been a little bit difficult to run that up until now, because up until a few weeks ago, it didn't download the providers for you. You either had to compile them to work with 0.12, or you had to download them manually. But it should hopefully be exciting once it does eventually land. I think they're on release candidate 1 at the moment, so it may be maybe a month or more before we actually get that. So even more advanced, all relating to Terraform state. Terraform allows you to specify remote state. So if you're working with a team of people, you don't really want to have the state in the same directory as the .tf code. Even if you check that state into version control, that relies on people always pushing the state to the shared repository and always pulling it down before they do a run. And if two people are doing a run at the same time, then you could end up in quite an ugly situation. So Terraform allows you to configure your state to be remote. So your state could be in S3 or in Azure Blob Storage, in HashiCorp's console, things like that. And a lot of those backends actually support locking as well. So if you're using that remote state and somebody else is doing a Terraform apply on that same project, then they won't be able to access the state. Terraform also allows you to import resources into it. So if you define an EC2 instance in your code, and there's already an EC2 instance there that you want to manage through Terraform, then you can use the Terraform reference, so that AWS_instance.name with the ID of the instance in AWS to actually import that into your state, which I think is one really a big benefit over a lot of the other cloud infrastructure tools. And Terraform also allows you to move resources around. So if you refactor your state, if you refactor your code into modules, then those addresses of the resources are going to change in the HCl, and Terraform may say, oh, this has changed, so I need to destroy this and recreate it, whereas you can just move those references around. Manipulating the state and working with the state can get a little bit hairy. And I'd say it's actually one of the reasons why you might not want to use Terraform. If you've got quite a simple project and it only uses one cloud provider, so if you're only using AWS, for example, then you may be better off using CloudFormation, which doesn't support a lot of the cool stuff that Terraform does and isn't as nice at expressing that infrastructure, but it does manage your state for you. So Terraform is a very useful and very powerful infrastructure as code tool, which allows you to manage your virtual infrastructure. It allows for code reuse. It allows for consuming other people's code to reduce the amount of work that you have to do. And I hope this has given you a good enough overview of Terraform to go away and actually be able to do some real damage in your own cloud accounts. You are now largely initiated. Thank you.